This video is intended for entertainment and historical purposes only. It's not meant to be an instructional tutorial or provide professional advice. Today we're back in the yard where we're going to be dropping side rods, pulling driving boxes, and releasing spring gear. Then, later in the episode, we're going to use an obscure tool called a wheel gauge to check the condition of the locomotive's wheel profile and tires. Locomotive side rods serve a singular purpose of transmitting power between all the drive wheels equally. The Davenports use a split bearing style of side rod, which is made up of 13 individual parts. These include the rod itself, 2 straps, 1 at each end, 4 bearing halves, 2 at each end, 2 wedges, 1 at each end, and 4 rod or strap bolts, 2 at each end. When all the parts are in good condition and tight, this becomes a very rigid assembly. However, this style of rod is prone to coming loose over time and requires regular visual inspection and hammer testing. The wedges each have a little grub screw. This is the first item to get loosened. As you can see, the wedge is pretty tight, so we'll move over to the rod bolts. Using a soft hammer, the tapered bolts are gently released from their fit. The assembly has now lost most of its rigidity, and the wedge comes out fairly easily. The straps are meant to fit very snug, and as you can see, they certainly do. The center-to-center distance of the rod bearings is critical for proper operation of the engine. Too much or too little distance can cause a whole host of problems, including overheating, excessive wear, or complete failure. Shims are used to position the bearings at a proper distance from each other, and the wedges are there to take up slack and keep things tight. The back rod bearing comes apart virtually the same as the front, the only difference being the location of the wedge. The side rod wedges are positioned in such a manner that they bear against the back of the rod bearings, and just like the pedestal wedges from episode 4, they take up wear towards the front of the locomotive. When you're removing multiple component parts like this, it's always good practice to put everything back together for storage. That way, nothing gets lost or forgotten. These parts might all look alike, but they're actually slightly different due to wear over time. That's why it's so important that everything goes back where it came from. The first thing we encounter on the left side is the bent wedge on the back bearing. I gave it a tap with the rubber hammer and promptly broke it. Fortunately, it doesn't need to be removed to get the strap off. I was a little concerned that the left side rod would be tricky to come apart due to how bent the rod is. But really, it wasn't too bad. The front strap bolts definitely required more encouragement in the form of a bigger hammer. But all in all, they weren't bad. With the rods off and laying on a flat platform, you can really see just how bent the left side rod is. Not a big deal, however. The Dinky's rods are basically just low-quality A36 steel, so it'll get bent back and normalized later on. Moving over to the drivers, it's time to pull the driving boxes and dope cellars. The driving boxes serve a multitude of purposes. Of course, their primary task is to be a wheel bearing. This is accomplished through the crown brass, a horseshoe-shaped brass bearing pressed into the driving box, which sits on the driving axle. They also determine the lateral or side-to-side motion of the drive wheels through the use of hub liners, which rub against wear surfaces on the wheel. The Davenport hub liners are made of babbitt, which was cast right onto the box. Lubrication for the crown brass and the hub liner comes from the dope cellar mounted under the axle. The cellars provide lubrication and keep the legs of the driving box from compressing inward. They're a snug fit and are held in place by just 2 pins. Using my special cotter key extractor, the cellar pins are gently tapped out. You can see how snug the fit is between the box and the cellar. With both pins out, the only thing holding the 60-pound box from dropping to the ground is the cellar and its fit between the legs of the box. For whatever reason, there's a mix of oversized cotter keys and L-shaped pins holding the cellars in place. I assume the pins are original to the locomotive, but frankly, I prefer the cotter keys for ease of removal. In steam locomotive speak, the drive wheel with which the connecting rod attaches is generally referred to as the main, or the main connection. On larger locomotives, the main will generally have a larger diameter axle and heavier driving box. This is not the case with the Dinkies, as the axles and driving boxes are all identical. At first glance, the driving boxes look nearly new, just very dirty. Here's the Babbitt hub liner I mentioned earlier. And this is the crown brass.
Meanwhile, in other parts of the works, the repair of the parts has been proceeding. In the white metalling shops, the axle boxes and bearings are being remetalled and the bearing surfaces machined and finished. After machining, the surfaces are burnished to a high polish.
Did you notice the molten hub liner Babbitt in the clip? Thankfully, I don't think we'll need to be doing that. The crown brass has oil grooves machined into the bearing surface to retain lubrication. The dope cellar is stuffed full of cotton waste, otherwise known as dope, which acts as an oil reservoir. In the railroad industry, this would be referred to as a plain bearing. In today's world, the vast majority of railroad equipment uses roller bearings, although you can still find plain bearings in use as diesel locomotive traction motor suspension bearings. An interesting fact about plain bearings is their efficiency versus roller bearings. Because the bearing literally floats on a skim of oil, its coefficient of friction is significantly less than that of a roller bearing. Unfortunately, this doesn't make up for the added maintenance required for proper operation. The wheels are now ready to go for sandblasting and paint. Then the new 2-piece eccentrics will be mounted to the axles, and we'll be ready to start assembling pieces as they're fixed. Moving over to the frame, it's now time to strip the spring rigging. The frame is still upside down from when we removed the cylinders to make the job a little easier. Locomotive suspension systems are generally referred to as spring rigging, and they consist of the following parts: springs, spring hangers, hanger shoes, gibs and pins, equalizers, and front or lateral equalizers. And we'll give honorable mention to spring saddles also. These are what connect the spring gear to the driving box. Notice how tight the pin is when I tap it with a hammer? The spring rigging on these engines is entirely held together by tension, meaning you must compress the springs to a point where you can pull one of the pins out. Then the spring is carefully released and you're safe to remove the rest of the parts. Big engines have a fully equalized system where every spring is connected together through equalizers. Little engines like the Dinkies are a bit different. The front wheels share a lateral equalizer and the back wheels are completely independent. Leaving the frame upside down allowed me the ability to use a jack and chain to release the springs. We don't need to compress the spring by much, just enough that it isn't in contact with the gib. Spring rigging is a fascinating science, right up there with boiler making and axle grease cake lubrication. Each wheel of the locomotive is designed to carry a given amount of weight, which is transmitted from the spring rigging to the wheels. This weight distribution can and does change. Take this gib pin, for instance. Over time, it might end up wearing down by 1/8 of an inch. At the same time, the legs of the spring saddle, which sits on the driving box, have worn a 1/16 of an inch. Maybe we've also machined another 1/16 of an inch off the crown brass. All these changes impact the weight distribution and can cause wheels to run warm or even overheat. Like I say, this is a fascinating but very complicated topic we'll save for another day. Spring rigging is very often overlooked by those in charge of oiling the locomotive. It can be hard to access with an oil can, or in the case of the Dinkies, there aren't even any lubrication holes where oil could be added. Add in the tight tolerances, and you've got a situation where problems are bound to occur over time. In the case of large locomotives with fully equalized spring rigging, these problems could present themselves as rapid wear to various parts. In our situation, however, because the Dinkies have independent suspension systems, we could see the potential for derailments increase due to the spring rigging seizing up and failing to apply enough weight to a particular wheel. You may recall from an earlier episode that I discussed replacing all 4 springs on this engine. Now that I've seen how much spring is left in them, I'm thinking they may be okay for service. Ultimately, I'll get them checked at a spring shop, but for now, I'm cautiously optimistic. The spring rigging parts get marked which side they're from, left or right, and which wheel, 1 or 2. When you're doing a project like this, you'll never regret marking every single piece, no matter how intuitive it may seem during disassembly. There's no worse feeling than putting a machine back together and having a couple random unmarked parts left over. In good condition, this spring saddle should fall to the ground by gravity alone. There should be no need for a hammer. Honestly, if everything was in good condition, it should all come apart without the use of a hammer. Like everything on the engine, no 2 parts are the same. All of the gibs and half the hanger pins came out like they were put in yesterday, but the front equalizer pins and the other hanger pins basically welded themselves in place. There's really no rhyme or reason why some pins corroded so badly versus others being like brand new. The only thing I can think of is the lack of lubrication many of these pins suffered from. These front equalizer pins were awkward to access, so they probably haven't seen a drop of oil since they were brand new. Check out the wood shims between the hanger shoes and the frame rails. This is one way of bringing the weight distribution back to standard. You lost a 1/4 inch through wear, so you add a 1/4 inch in shims. The fact that all 4 shoes have these shims indicates that either the axles, crown brusses, or tires have been machined at some point. The final 4 hanger pins all suffered from the same stubborn disposition, requiring a combination of hammer blows, heat, the use of a puller, more hammer blows, and more heat. Reluctant right to the bitter end, the pins even needed a little encouragement with an angle grinder. The final part of the spring rigging to come apart is the equalizer. After spending a significant amount of time off camera trying to get the pins out, I decided to just drill a large hole 3/4 of the way through the pin in hopes that between the hole and the heat and beat cycles, it would finally release. Well, it turns out that was a waste of time. The equalizer hangers are just 2 strips of flat steel, so I'm not overly concerned about saving both of them. I would like to preserve one as a reference, however. Using a chisel, I was able to bend one of the hangers enough that I could turn it away from the pin with hopes that it would now hammer out. With no other options, I brought out the cutting wheel. There you have it. The spring rigging is in a pile, and the frame is ready for sandblasting and paint. The next time you see all these parts will be during the reassembly phase. Now, let's talk about wheel and tire gauges. But first, for those of you who don't know, here are the basic parts of a railroad wheel. Specifically, a steam locomotive wheel, its tire, and some common condemning defects. Steam locomotive wheels are generally made out of cast iron or cast steel. They then have a steel ring known as a tire shrunk on. The tire has the wheel profile that we'll be checking machined into it when new. As with cars, the locomotive tire eventually wears out and gets replaced with a new one. Looking at the tire profile, we have the flange, the tread, and the tire thickness. Common ailments include tread worn hollow. This is when the tread starts to wear into a dish shape. Wheel tread normally has a slight taper from the flange to the rim to help the locomotive track through curves. This defect increases running gear wear and, if severe enough, could cause a derailment. Thin flange. Over time, flanges become thinner due to normal usage. High flange. For today's discussion, we'll focus on one type of high flange, which is really just a combination of tread worn hollow and a thin flange. The only way to correct these issues is to mount the wheel set in a wheel lathe and machine a new wheel profile. Depending on how bad your wheels are, you might need to machine off so much material that the tire thickness hits its condemning limits. The first gauge we're going to look at is what's referred to as a thin flange gauge. It's basically a go, no-go gauge with two separate minimum thickness slots. This is an older gauge, so it's slightly different than what's commonly in use today. Modern gauges will generally have a 7/8 inch slot and a 15/16 inch slot. If you can fit this over the flange and touch the tread with this leg, the wheel's condemned. Like the locomotive inspector's hammer, you can also check coupler contour and a couple other freight car specific things with this gauge. But really, it's not that useful for the steam locomotive mechanic. The next gauge we're going to look at is what's known as a finger gauge. To use this gauge, we place the leg on the tread with the spine tight against the back of the wheel. The hooked finger is turned to measure flange thickness like this, and flange height like this. My flange thickness is just fine, but let me show you what condemning looks like. As you can see, this is a pretty useful tool, but again, it's much more freight car and diesel locomotive specific. For our purposes, we need to use a proper steam locomotive tire gauge. This complicated little gauge measures flange height, flange thickness, tread worn hollow, and tire thickness in a single operation. This arm extends down from the tread and catches on the lip of the tire where it meets the wheel. This gives us an exact tire thickness reading. The tires on this engine appear to have been turned at least once, but they're still over 1/4 of an inch away from condemning limits. This might not sound like a lot. However, because the tread and the flanges are like new, we should get many years of service out of these tires. These pointers extend to measure tread worn hollow and flange thickness. Unlike the other wheel gauges, this one gives the ability to see how dish the tread is before it hits condemning limits. This was a very basic overview on wheel gauges, and I left a lot out for the sake of keeping things simple. If you'd like more details, I suggest looking up AAR and FRA documentation on the subject. Now that engine number 1 has been fully torn apart, we can turn our attention to engine number 2 and the push towards its boiler inspection and ultimately its steam test. Additionally, it's time to start working on other activities such as pattern making. In the coming episodes, we're going to start the Herculean task of making the many new wood patterns required for both locomotives. This will be accomplished through the use of everything from prototype CNC routers to plain old sandpaper. We'll follow the process from drawing to final casting and hopefully demystify a few things along the way. Thanks for watching right to the end of the video. If you're enjoying the project, please consider subscribing, leaving a comment, and giving the video a like. None of that costs you anything, but it goes a long way towards building the channel. Here are a couple other episodes from the series you might enjoy.